Alright, so here we go. We're going to continue on with our example. Now, the alpha being 0.05, that means that that's going to get our bell curve. We have that the null hypothesis, or the alternate hypothesis, is a two-tailed test. So we need two tails here. And we know that total area for the shaded region is 0.05. Okay, now the thing that we just did was we found we had a z-value. We don't know where it is. Maybe I'll put it here. The z-value, and when we looked up that area, or this whole area, is the 0.9706. But we want the tail. We want this blue portion here. We want the tail, and we can figure that out. All you got to do is 1 minus 0.9706, and we get 0.0294. But it's a two-tailed test, so we want to multiply that by 2 so we can get some blue area over here too. And so we have some blue area, and then this blue area, we want that also to be 0.0294. Okay, so when we add the two blue areas up, so we got 0.0294 plus 0.0294, we get 0.0588, and so that's the area for our blue region. When we compare it to the area of our alpha, we have that that's bigger. The blue region is bigger. So this is the blue, and we have that that's bigger than 0.05. Okay, so what's that is telling me in our original picture here, we have our z-value that we found, which was the 1.89, is actually in the non-critical region. Okay, so what does that mean? That means that we want to accept the null hypothesis. Okay, and that was the claim. So the question was asking, thus, claim is true. Alright, so it says, is there enough evidence to reject the claim? And then we would say, no, there is not enough evidence. And there we go. So it's like, which way do you prefer doing it? Do you like the p-value method, or do you like our other method that we were doing? It's up to you, whichever one you want to use. So there's a couple more things that I wanted to say. And basically, sometimes you have p-values, but you don't know what alpha is. So here's some different cases. You guys can pause the screen and write it down. But it says, if the p-value is less than or equal to 0.01, then you reject the null hypothesis no matter what, because the difference is highly significant. If it's bigger than 0.01 and smaller than 0.05, then you reject the null hypothesis. And then if it's bigger than 0.05, you kind of have to deal with the consequences. If it's bigger than 0.10, you do not reject the null hypothesis. There's not a big enough significant difference. All right, and then finally here we got some statements about significance. So pause the screen and read it, and then we'll move on to 8.3. All right, so these chapters are going along, and it's similar to the last chapter where, well, the chapter that we had z-test and then we did our t-test. So this was our new table. So our second table. All right, so this is when our sigma is unknown. We use our t-test. And so this is our equation that I want you guys to remember. I will give it to you. We got our degrees of freedom, which is our favorite equation. You just subtract 1 from whatever your sample size is. And then if the sample size is above 30, you could still use this formula, and you want to just look at the nearest value. Okay, they are pretty conservative here though, so you should round down. Let's do some examples here. So just reading the table, if you had a right-tailed test and we had the alpha is 0.05, so right tail, we got our area is 0.05, and our degrees of freedom was 16. Alright, so we'd use our table, make sure to look at the one tail portion for the 0.05, and then go down to the degrees of freedom, go across, and we find our t-value. Similarly, if you had 0.01 degrees of freedom, 22, left tail test, it's going to be one tail again. So you look at the one tail row and then find where they intersect, and we get the t-value. This, I would suggest that on your t-table to go ahead and verify that you get that t-value. And then we have down here for the next example, alpha equals 0.10, degree of freedom is 18. However, it's a two-tailed test, so we want to look at the two-tail row, go to the 18 for the degrees of freedom, and you get two critical values, here and here. Okay? Alright, so for the two-tail test, things are going to be symmetric, so you want to make it positive and negative. Alright, so let's do an example here. So let's read it. So we got, this example is talking about hospital infections. A medical investigation claims that the average number of infections per week at a hospital in southwestern Pennsylvania is 16.3. A random sample of 10 weeks had a mean number of 17.7 infections. The sample standard deviation was 1.8. Because we don't know what the population standard deviation is, that's why we're doing the t-test. Is there enough evidence to reject the investigator's claim? Alright, so reading through this, we got mu is 16.3, which is our null hypothesis. And remember that they're claiming that the average of number of infections is 16.3, so that's why we have it being our claim. The alternate hypothesis is that it doesn't equal 16.3. We want to see if there's a significant difference here. So we go ahead and find our critical values, because we got alpha equals 0.05, our degrees of freedom is 9, and we have a two-tail. So if you look at our table, you're going to see that you get 2.262 and negative of that. Remember, it's a two-tail, so it's positive or negative. Those are our two values. Okay, so then we're going to substitute in for our t-test. So really, this should be a t here. T, we substitute in x bar, mu, s, and square root of n. Remember, s is the sample standard deviation, and we get 2.46. Now we're going to have to keep that in mind. So when we use the table, we got our t-scores here, and then when we found our t-test, our z-score here was 2.46. And so you see that the 2.46 is bigger than the 2.262, And so we're in the critical region. All right, so then we're going to reject the null hypothesis. And which was the claim. So reject the claim, like our sentence says, that the average number of infections was 16.3. So there's enough evidence to so that we can reject it.